All right, let's dive in. Today we are tackling one of the trickiest but also one of the most important topics in software, concurrency. It's basically the art of getting your system to juggle a whole bunch of things at once without, dropping all the balls. So let me ask you this. Have you ever built a beautiful, speedy application, but the second it starts getting popular, the whole thing just slows to a crawl? Yeah. Clicks take forever, pages just hang, and your users get super frustrated. It's a classic problem. And the real reason it's happening is probably not what you think.
The best way to think about it is like a digital traffic jam. Imagine a user desperately needs a password recovery email. That's a tiny, urgent task. It should be instantaneous. But at the exact same moment, your system is chugging away, generating some massive 10-minute-long monthly report for another user. If they're both stuck in the same lane, well, that urgent email is now stuck in a 10-minute traffic jam. And that is the core of our problem.
So to solve that traffic jam, we first need to be speaking the same language. It's not enough to just say the code is slow. We need to get really specific about how operations can overlap and interfere with each other. And that brings us to a couple of core concepts we absolutely have to understand.
Okay, first up, concurrency. Now, here's a super important point. Concurrency doesn't mean two things are happening at the exact same millisecond. It just means their execution overlaps. Task A might start, and then task B kicks off before A is finished. It's right there in that overlap that you get all the power and all the danger of concurrent programming.
And this right here is the danger zone, the critical section. Think about a simple counter in your app, maybe counting page views. That little piece of code that reads the current value, adds 1, and then writes the new value back, that's a critical section. If two threads try to do that at the same time, they might both read the number 50, both add 1 to get 51, and both save 51. You just lost a page view. That's a race condition, and it's exactly why we need some strict rules for this zone.
So, how do we manage these digital traffic jams and protect those critical sections? Well, a lot of the time, the simplest strategy is the best one. Just avoid the conflict entirely. Instead of making everyone share one road, let's just build some more highways.
This is a really powerful architectural pattern called workload isolation. It's all about preventing the noisy neighbor problem. You don't want one huge resource-hungry task slowing everything down for everybody else. By creating separate processing lanes or queues for different kinds of work, you make sure your fast, critical tasks always have a clear express lane.
And this isn't just theory. Here's a super practical example using a popular tool called Celery. Step 1, you just create a new queue. Maybe you call it slow_queue. Step 2, you start up a dedicated worker process whose only job in life is to listen to things on that new queue. And finally, step 3, you just tell your app to send all those heavy report-generating tasks over to the slow queue. And just like that, your password reset emails are flying by on the main queue, totally unimpeded.
But what happens when you can't build separate highways? What if two tasks absolutely positively have to access the exact same resource, like that shared counter we talked about? Well, for those times when sharing is just unavoidable, you need a system for taking turns.
And this is where locking comes in. A lock is kind of like a key to a room. Only the thread holding the key is allowed to enter that critical section of code. Everybody else? They have to wait outside. This principle is called mutual exclusion. It guarantees access is exclusive. One at a time, no exceptions. The real question is, what's the best way to wait your turn?
You've basically got two choices. First, there's the spin lock. This is like an impatient kid in the back of a car, just constantly asking, are we there yet? Are we there yet? Are we there yet? It just burns through CPU cycles over and over, checking if the lock is free. Then there's the much more polite queue lock. This is like forming an orderly line. The system actually puts the waiting threads to sleep and then wakes them up only when it's their turn. It's way, way more efficient if you expect the wait to be anything more than a few microseconds.
But wait, we can get even smarter. Check out the readers-writers lock. This thing is brilliant because it recognizes that not all access is created equal. I mean, if a dozen threads just want to read a value, who cares? There's no conflict. So this lock lets all the readers in at the same time. But the second a thread shows up that needs to write a new value, boom, it gets exclusive access and everyone else, readers and other writers, has to wait. For workloads that are mostly reads, this is a huge performance boost.
So we've got isolation, and we've got a few different kinds of locks. This brings us to the most important part. How in the world do you choose?
Well, it all comes down to understanding the trade-offs. And for that, you need a clear decision framework.
This quote perfectly captures the philosophy behind traditional locking. It's called pessimistic because you basically assume a conflict is probably going to happen, so you lock the resource before you even start your work, just in case. It's definitely safe, but it can be slow if it turns out conflicts are actually pretty rare.
This slide lays out the fundamental trade-offs really well. With coarse-grain locking, you have one big lock for everything. It's simple, but it can easily become a massive performance bottleneck. With fine-grain locking, you use lots of smaller locks for higher performance, but it's way more complex and you risk deadlock, which is a nightmare where two threads get stuck waiting for each other forever. And finally, you have optimistic synchronization. This is where you don't lock at all, you just try the operation and check for conflicts afterward. It's crazy fast for read-heavy situations, but you risk starvation, where a task gets stuck retrying over and over again. The crucial takeaway here is this: you must match your strategy to your workload.
All this complexity with locks and deadlocks and all these trade-offs has led a lot of smart people to ask a really fascinating question. Can we get the safety of concurrency without having to manage all this stuff ourselves? And this brings us to the horizon, a potential future without locks.
One of the most promising answers is something called transactional memory. The idea is to let developers wrap a bunch of operations in a transaction. You just tell the system, hey, make this whole block of code happen atomically. The system then figures out how to do it, using optimistic techniques under the hood and automatically retrying if there's a conflict. It's an attempt to give us the best of both worlds: simple code and amazing concurrent performance. And that really leaves us with a final thought. Concurrency is a fundamental challenge that only gets harder as our systems get more and more parallel. So, are we heading toward a future where clever abstractions like transactional memory make locks totally obsolete? Or is the basic problem of who goes next so baked into computing that we'll just always be designing new, more sophisticated ways to manage the queue? That's the question that's going to shape the next generation of software.